Okay, so for this next set of notes, we're going to talk about the thermodynamic processes that an ideal gas can go through. So what I'm going to want you guys to do for this is for each process, imagine a fixed amount of ideal gas in a movable piston. So this is kind of like what I talked about in the last set of notes. Imagine here we've got some gas in there, we got our particles moving around, and there's a piston here that can be moved in or out either way. Okay, so we're going to make a big chart over here, so make sure you give yourself enough room on your paper. There's going to be 4 different processes that we go through, and then we'll have some graphs that go along with them. So the first process we're going to talk about is an isothermic process. And in an isothermic process, we have no change in temperature, which means there is no change in internal energy. The way you can tell that, iso meaning same or one, thermic meaning temperature. So a description of what this one is, you can add heat to the system and then have the system do work. So work by the system. The other way you can do it is remove heat and do work on the system. So when we are thinking about our little piston, we can either put it next to something hot and then allow it to expand, or we can put it next to something cold or put it near colder surroundings and then push in on the piston to compensate for that loss in energy. So let's look at what the graph would be here. We have our PV graph. We have pressure here. We have volume down here. What you're going to see is that an isotherm makes one of these. And this should look pretty familiar from what we've done with ideal gases. If here is temperature A, and here is here is point A, here's point B. These are all the same temperature because it's an isotherm. Then this area underneath right here, this is going to be the work. So if you're going this way, your volume is expanding. That's work done by the system. That's where you have to add heat. If you go from B to A, that's where work is being done on the system because you're losing heat. If you wanted to go to a higher temperature, it would just look something like that. We'll call that T2. Same idea. It's just more energy, higher temperature, higher the curve, lower energy, lower temperature, lower the curve. The next one we're going to talk about is an adiabatic process. So in an adiabatic process, there is no heat change or no heat added or removed from the system. A just means without, abatic relating to heat. So adiabatic without heat. In this case, what is happening? Remember that our equation is delta U equals Q plus W. In this case, Q is 0. So what it tells us is that our change in internal energy is just going to be equal to our work. So what does that look like in the real world? It means that our gas doesn't absorb or release heat, meaning the process is usually quick and or very well insulated. Let's draw the graph and then we'll come back over here to work on the description again. So in this case, it looks very similar to our PV diagram for isothermal. However, the one difference this time is that it's much steeper. So I'm just going to put a little note here. Steeper than isotherm. And the reason for that is in this one, you're going to be losing energy. Your internal energy is going to go down. If you do work here, this is work by the system. If I go this way, I'm going to be losing energy because doing work means I have a negative delta U. My temperature is going to be dropping. That's why I go from one isotherm down to a lower one. So that's an important thing on there. So just like we said before, I'll just go through here. If I go from A to B, then what's going to happen is that I have negative work, which means I have negative delta U, which means I have negative delta T. So there you go. The opposite is true when I go from B to A. I'll have positive work, which means I'll have positive change in internal energy, which means I'll have a positive temperature change. And you can tell that just by looking at it, even if you just think about ideal gases. If I'm going this way, then I have a change in volume that's positive. Usually when a gas expands, everything else stays constant, then it's going to lose its temperature. The pressure is going to go down. If volume goes up, pressure and temperature go down. Opposite's true if I go the other way. My volume gets smaller, I've squeezed it into a tighter area, pressure and temperature go up. Next up, we have the isobaric process. In this one, it means you have no change in pressure. Iso meaning same, bar relating to pressure. So what does this look like? Well, in this case, we get to use the full equation because our heat and work are not going to be limited. So when we look at our PV graph, since it's the same pressure, we'll just have a line right across here. So we'll have A, we'll have B. Hopefully that's all on there. Cool. So in this case, we have to maintain the same pressure. If we go from A to B, so for instance, going from A to B, we have to increase our internal energy. Here I'll just say it's greater than 0. So that means that our temperature is going up. And so to do that, with our volume expanding, that means that our work is going to be negative. Volume expanding, work is less than 0. Because the system is doing work, it's expanding, it's pushing out, it's releasing energy into the world. So if our volume goes up, work is negative. That means that our Q has to be greater than W. So Q is going to be positive and greater than W. That means we're adding more heat into the system than work is being done by the system. The opposite is true when we switch it over. We have a negative delta U. Temperature is going down. Volume is going up. Our work is being done on the system, which means we are releasing more heat than we're doing work. Finally, we will have isovolumetric. This one should be pretty self-explanatory. It is no change in volume. Iso, volume, same volume. This one can also be written, thank you, Bell, as isochoric. So be ready to see it either way with that one on a test. And what does this one look like? If we have no change in volume on our PV graph, it means we're just going straight up and down. A, B. So in this case, if volume doesn't change, the system isn't expanding or contracting, meaning no work is being done. So if we look at the normal equation, delta U equals Q plus W, W equals 0. So we are only changing our internal energy based on heat. If you remember, so delta U equals Q. If you remember our equation from the last unit, the internal energy is 3 halves PV. In what it's going to look like here, if we go from A to B, in this case, our pressure is just going down. What's that? Sorry, I have it flipped. From A to B, yeah, our pressure is going down. Never mind, I'm right. So pressure down, which means that our internal energy our change in internal energy is going to be negative. It means our temperature is going down, which means we have to remove heat. Opposite is true when we go the other way. Pressure goes up, internal energy is positive, the change in it, our temperature is going up, which means we have to add heat. So think of it this way, if we take that piston and we hold it in place so it can't move, and we either add heat, in which case our pressure is going to go up because our temperature is going to go up, or we're going to remove heat, which means our internal energy goes down, temperature goes down. Okay, so now let's talk about, we've talked a little bit with work in those processes that we just talked about, but we're going to look at what it actually means when we're talking about the pistons. In this first case, I've got a piston, and if you need time, go ahead, pause it, draw these. I've got a piston where I'm going to push it from this position down to there. In this case, the volume of the gas inside is going to decrease, so negative delta V. When that happens, I'm having to push. I'm adding energy down into that system. Work is being done on the system. So this is work done on the system. This is what's called compression. So when we're talking about gases, work is done on a system when you are pressing down. Over here, I'm taking my piston and I'm moving it up. I'm not pulling, the system itself is doing that work. So in this case, I have a positive change in volume, which is going to lead to a negative work. This is work done by the system. It's using its energy, and this is where we get negative. So if there's nothing else happening here, then we're going to have a negative internal energy change. And this is what's called expansion. So when we remember that work is just force times distance, this is always perpendicular for our purposes here, so you don't have to worry about any cosines. But when we do that, we can break force down. Force from our fluids unit, we should remember, is pressure times area. So we have PAD there. A times D, so that's meters squared times meters. Hey, that sounds a lot like volume. What we find is that work is equal to pressure times change in volume. Using that, I want us to figure out for the two graphs that I'm about to draw, what is the work done? The work done on the following graphs. So here we go. What is the work? And I want you guys just to take a second, pause when I get to it, and I want you to fill in the area of the net work done by the system. So here's a PV graph, and I'm going from A to B. I want you to, on the graph, show me the area where the work is. Take a second, I'll come right back. Hopefully you guys got it based on what we just did with that equation, that it's going to be the area under the graph. So this would be the area of your work. Now in this next one, I want to know the net work done by the system, meaning it's going to have two steps and they won't be the exact same. So first step, we're going from A to B. Looks like this. A to B. We're going high pressure, changing volume, and then going down pressure once we get to that volume. Then the second step, what we have is this. We're at lower pressure going up to that new volume. So I want you to first show me the work done for each step, and then show me what the net work is going to be by the system. Okay, so first thing I want to do, draw my lines. One interesting thing to note, if I start and end at the same point, I have no change in internal energy. Meaning that if I look at this as a whole, this would be an isothermal process. Each step is not isothermal, but the reaction as a whole would be. So this area under here is the work of process B to A. Let me finish those lines. Now, the area under this graph here is going to be the work done by process AB. You'll notice that one's a lot bigger. This up here, This difference between them, this is the net work. When you look at it, since it's expanding, this is work done by the system. Since expanding, work done by, contracting, work done on. So the system would have a negative W for the whole process. One of the ways 2 years ago my physics students said they remember it is that when you go clockwise, that is work done by a system, and then when you go counterclockwise, it's work done on. So they say by the clock, on the counter. That's the way they remembered it. If that works for you, go for it. If not, just remember it physically. So now let's derive the Boltzmann equation, and we're going to derive from the Boltzmann equation and the ideal gas equation. So let's do that. We will have Boltzmann and ideal. When we combine those equations, I mean, the derivation's not supremely important for us, but what we get at the end is that delta U is going to be equal to 3/2 KB, sorry, just writing down Boltzmann there, 3/2 delta PV, or delta U is equal to 3/2 P delta V. Remember the units of this are joules, pascals for pressure, and cubic meters for volume. So just like I said earlier, up at the top, this cycle here. So if a gas undergoes a complete cycle, delta U equals 0. It ends up at the same temperature it was before. It should have the same internal energy. We call this a Carnot cycle. Why is there a T in there? Because the French language is disgusting. But that'll do it.